Welcome to AI News Digest 2026-0603. Today's 12 stories. Story 1, Google I/O 2026 showcases Gemini AI and agentic features. Gemini 3.5 Flash now available. Story 2, Thinking Past the Answer, Evaluating Harmful Overthinking in Large Reasoning Models. Story 3, What Benchmarks Don't Measure, The Case for Evaluating Abstention Competence in Autonomous Agents. Story 4, Visual Graph Scaffolds for Structural Reasoning in Large Language Models. Story 5, Handoff Debt, The Rediscovery Cost When Coding Agents Take Over Interrupted Tasks. Story 6, ChatHealthAI, Aligning Electronic Health Record Representations with Large Language Models for Grounded Clinical Reasoning. Story 7, Everything Announced at Microsoft Build 2026, AI, Windows, Surface, RTX Spark, and more. Story 8, Don't Gamble, Gamble, An Analytical Framework for AI-Driven Research Systems. Story 9, When Helping Hurts and How to Fix It, Multi-Agent Debate for Data Cleaning. Story 10, Toward a Modular Architecture for Embedded AI Agent Systems at the Edge. Story 11, OpenAI warns US could fall behind China without copyright reform for AI training. Story 12, Aura, Action-Gated Memory for Robot Policies at Constant VRAM. Researchers Marcus Rube and Michael Gerhartz have published a new paper on Archive, proposing what they call a modular reference architecture for embedded AI agent systems at the edge. Filed on June 1, 2026, the work tackles one of the most persistent blind spots in modern AI research: the fact that almost all of today's agentic AI frameworks assume access to server-class hardware or a reliable internet connection. That assumption breaks down for the billions of microcontroller-class devices that power everything from industrial sensors to medical monitors and smart home gadgets. The core idea is a tiered design that splits the intelligence stack into two layers. On-device agents handle time-sensitive, privacy-critical tasks using compressed neural networks and rule-based logic, running entirely on the local chip without needing cloud access. Cloud-augmented agents, on the other hand, tap into small language models for more complex reasoning and planning when connectivity is available. Crucially, the two tiers are designed to decouple cleanly, so the device remains functional and safe even when cloud access drops. What makes this paper particularly forward-thinking is a third component the authors call the governance layer. This is a cross-cutting system that runs across entire fleets of distributed autonomous devices, providing observability, policy enforcement, and safety guarantees. As regulators in the EU and elsewhere begin to demand explainability and auditability from autonomous systems, the governance layer concept could become a foundational requirement for any commercial embedded AI deployment. The authors are honest about what this paper is and is not. It does not present experimental benchmarks or performance numbers on real hardware. It is a design and architecture paper, offering principles and trade-off analysis rather than a ready-to-deploy toolkit. That is both its strength and its limitation. On the strength side, it gives the broader community a shared vocabulary and structure for a problem space that has been largely fragmented. On the limitation side, engineers looking for concrete guidance on which microcontrollers to target or which SLMs to use will need to look elsewhere. The implications are significant for the IoT and embedded AI industries. Companies like ARM, ST Microelectronics, and Nordic Semiconductor, who supply the hardware for these constrained devices, may find this architecture a useful reference as they develop AI-capable SDKs. More broadly, as the SLM ecosystem matures with models like Microsoft's Phi Series targeting edge hardware, the cloud-augmented tier described here becomes increasingly practical. This paper may well be cited as an early landmark when the history of embedded agentic AI is written. In March 2025, OpenAI made a dramatic and explicit argument to the United States government: reform copyright law for AI training data or lose the AI race to China. The company submitted formal comments to the U.S. Trade Representative during the public input period for President Trump's AI action plan, and the language was unusually blunt. OpenAI stated directly that if Chinese developers have unfettered access to copyrighted data while American companies do not, the race for AI is effectively over. The submission frames what has largely been a commercial legal dispute. OpenAI and other AI companies face multiple active copyright infringement lawsuits from publishers, news organizations, and authors, as a matter of national security and geopolitical competition. By invoking China as the foil, OpenAI is attempting to recast the debate from one about intellectual property rights into one about American technological dominance. It is a strategically sophisticated move that aligns with the Trump administration's hawkish posture on China, while simultaneously arguing for lighter regulatory touch on AI data access. OpenAI is calling for a freedom-to-learn doctrine in U.S. copyright law, which would expand fair use exemptions to allow AI companies to train on copyrighted content without licensing or compensation. The company argues that the current approach of litigation and restriction yields little protection for original content creators anyway, while actively handicapping American AI developers against Chinese competitors who allegedly face no such constraints. That central claim deserves careful scrutiny. While China's enforcement of international copyright norms has historically been inconsistent, Chinese AI companies also operate under significant domestic content restrictions and political constraints on training data. OpenAI's binary framing of American restriction versus Chinese freedom may be considerably oversimplified. For content creators, journalists, and publishers, the stakes are enormous. A freedom-to-learn doctrine, if adopted, would effectively allow AI companies to scrape and train on any publicly accessible content without consent or payment. The implications for the economics of creative work would be severe. Policymakers will need to weigh American competitiveness against the rights of the human creators whose work underlies the training data powering these systems. OpenAI's lobbying ensures the AI industry's perspective will be impossible to ignore in that conversation. A new paper from researcher Joseph Chen, posted to arXiv in June 2026, introduces Aura, MEM, a memory management system designed specifically for robots running large AI models on edge hardware. The full name is Action Utility Recurrent Adaptive Memory, and the core problem it solves is deceptively simple to state but surprisingly hard to fix. The standard memory caching approach used in AI systems grows without bound as an episode gets longer, which works fine in a data center, but is disastrous for a robot that needs to run for hours on limited, fixed hardware. To understand why this matters, consider how modern AI language and vision models store context. They use what's called a KV cache, which keeps a record of every observation processed so far. In a cloud server handling short, discrete requests, that cache resets constantly and costs little. But a robot navigating a warehouse or performing surgery does not reset. Its episode can run for thousands of time steps, and at 100,000 steps, Chen's measurements show the KV cache would be over 6,000 times larger than what Aura MEM requires. Aura MEM maintains a fixed inference state of just 4,224 bytes regardless of how long the robot has been running. How does it achieve this? Through a learned gate that asks a simple but powerful question: would this new observation change what the robot does next? If the answer is no, Aura MEM stays silent and skips the memory write entirely. The gate is trained directly on action prediction error, not on reconstructing past observations, which means it is optimized for behavioral relevance rather than perceptual fidelity. This is a genuinely novel approach, and the experiments back it up. On the Liberalong robotic manipulation benchmark, Aura MEM matches the best baseline success rate of 0.233, while writing to memory 7 times less often. Importantly, random and periodic write schedules with the same budget could not replicate this efficiency, confirming that the action surprise signal itself is doing the heavy lifting. There's also a hardware durability angle here that often goes unmentioned. Flash memory, which many edge devices rely on, has a finite number of write cycles before it degrades. A system that writes 7 times less is, in theory, extending the hardware lifespan of the robot proportionally. For companies deploying robots at scale, that is a meaningful operational cost reduction. Aura MEM is a compact, but important step toward making large AI models viable for real-world, long-running robotic systems. This paper proposes using graphs not just as external knowledge sources for LLMs, but as internal reasoning scaffolds, analogous to how humans use mind maps to organize branching thoughts. The approach aims to improve structured and multi-step reasoning in LLMs. It represents a novel architectural contribution to improving LLM reasoning capabilities. This paper studies a real-world limitation of coding agents that existing benchmarks ignore: the cost incurred when one agent or engineer hands off an interrupted task to another. The authors define handoff debt as the rediscovery cost from opaque or incomplete prior work. This is highly practical for understanding where coding agents fail in real software development workflows. ChatHealthAI proposes a multimodal framework that bridges LLM's natural language reasoning with structured EHR foundation models for clinical decision support. The system grounds LLM reasoning in structured longitudinal patient data, addressing a known weakness of general-purpose LLMs in healthcare. This is a practical application of LLMs in high-stakes medical settings. Microsoft Build 2026 featured a range of AI-focused announcements, including new Windows AI integrations, Surface hardware with RTX Spark, and expanded developer tools. This continues Microsoft's deep integration of AI across its product stack. The event signals major product-level AI developments from one of the leading AI platform companies. This paper introduces Gamble, an analytical framework for understanding and improving AI-driven research systems, ADRS, systems that couple LLMs with automated evaluation to discover algorithms, proofs, and scientific designs. The authors argue that standard convergence guarantees are insufficient for these systems and propose better analytical tools, relevant as ADRS systems like AlphaProof and AI Scientist gain traction. This study rigorously evaluates multi-agent debate across 6,000+ task condition pairs and finds it degrades data generation performance while improving error detection. The paper identifies critique-induced confusion, CIC, as the failure mode and derives conditions under which debate helps versus hurts. This has direct practical implications for designing multi-agent LLM pipelines. This paper addresses the challenge of deploying LLM-based agentic AI on deeply embedded microcontrollers with severe memory and energy constraints. It proposes a modular reference architecture for edge AI agents that does not assume server-class resources or constant connectivity. This is an important open-source practical contribution for on-device AI deployments. OpenAI submitted to the U.S. government that without fair use access to training data, the AI race is effectively over for American companies, as Chinese developers face no such restrictions. This reflects ongoing policy and legal battles around AI training data that could significantly shape the competitive landscape. Sam Altman's organization frames copyright reform as a national security issue. Aura proposes a new memory architecture for embodied AI agents that replaces the standard KV cache with action-gated memory suited for long, non-resetting robot episodes on edge hardware. It addresses bandwidth and write endurance constraints specific to robotic deployments that data center-optimized inference systems ignore. This is a practical systems contribution for deploying LLM-based robot policies.